Hey, welcome back, folks, and welcome to our online students. Today what we're going to do is we're going to try to differentiate the enthalpy of reaction versus the enthalpy of formation. And they are very, very similar, and in fact, in some ways, they're interchangeable. And so what we'll do is we'll define what those two things are and then show how you can use them to solve some problems in thermochemistry. So that's kind of my goal, is by the end of this session, we'll be able to identify what's the difference, what are the similarities between these two, and then how to use them. So in this slide right here, it uses the word standard a lot. It's a standard enthalpy of reaction. And how do we know that it's standard enthalpy of reaction? Well, you see the little RXN in the upper right-hand corner there, and it has the degree symbol. That degree symbol means it's at standard conditions. And standard conditions means that this is at room temperature and room pressure, so 1 atmosphere and at room temperature. And some people will argue that standard temperature is 0 degrees Celsius, but it's hard to do chemistry at 0 degrees Celsius because most of our solutions are aqueous and water freezes around 0 degrees Celsius. That makes chemistry hard. So chemists, standard temperature and pressure, we say, is about 25 degrees Celsius. And then standard states. Standard states is the most stable form of a substance. So it's the form of the substance that we would see at room temperature and room pressure. So if I asked you oxygen, O2, O2 at room temperature and pressure would be a solid, liquid, or a gas? Gas, it would be a gas, okay. And then nitrogen, what would nitrogen be? At room temperature. It would be a gas. Excellent. And then H2O. How about H2O? What would that be at room temperature? A liquid. Generally, it would be a liquid. But water is a little weird. Could water also be a vapor at room temperature? Yeah, it can be. So water is a little weird. It could be a liquid, but it could also be a gas. But we would call these standard states. So how you would normally find the substance at normal temperatures and pressure. These are called our standard states. Now, enthalpies of reaction and enthalpies of formation. How do we tell these two apart? So I'm going to write out two equations here. One of them is going to be the enthalpy of reaction. The other is going to be enthalpy of formation. And we'll see if we can't tell the difference between the two. So I'll start out here with N2 gas plus O2 gas gives us 2NO, nitrogen monoxide gas. And there's some enthalpy involved in this. It says delta H RXN equals 180 kilojoules per mole. And then I have a second equation here, and it looks very similar. I'm going to go 1/2 nitrogen gas plus 1/2 oxygen gas gives us nitrogen monoxide, and our enthalpy of formation is equal to 90 kilojoules per mole. So here's my two reactions. They look fairly similar, and the way that I can tell which is which is I can see here that this here is enthalpy of reaction, and here I have enthalpy of formation because this one has an F, and that is RXN. So we can tell which one is which. But if I were to cover these up maybe like this, can you see a difference between these two reactions? What do you notice is different about them? Yeah. The bottom one is half of what we have up above. Yeah, it's half of what we have. It's like half all the way through, right? Even the numbers on the end are half. Good observation. So in general, do we say then that the enthalpy of formation is just half the enthalpy of reaction? And almost not, almost. Your observation is absolutely correct. Now the enthalpy of formation, it tells us here in this slide here that it's the change that takes place at constant pressure when 1 mole of a substance is formed. And so what we're looking for here is 1 mole. We have 1 mole being formed. It's 1 mole of product being formed. And so that is our enthalpy of formation. And really what that means is how much energy is gained or lost in producing 1 mole of product. 1 mole of product. And say put a star next to that. That's how you tell the difference between an enthalpy of formation versus maybe an enthalpy of reaction. The enthalpy of reaction could be more than 1 mole. And it could be more than 1 product. But we're looking here for just 1 mole of one thing. That would be our enthalpy of formation. That's how we can identify it. How much energy is involved in making this. Okay? The other thing is that these reactants here have to be in their standard states. So our reactants are in their standard states. So if this was liquid nitrogen or liquid oxygen, we say, well, that's not normal at room temperatures and pressures. So that would then not be an enthalpy of formation. So we're looking at our reactants have to be in their normal forms that we'd expect at room temperatures and pressures, and we are producing 1 mole of product. So a test type question might look like this. Can you identify which of these reactions is a standard enthalpy of formation? You take a look at these reactions, standard enthalpies of formation. So let's try the first one up there, A. Let's try A. So taking a look at A, does A meet our definition of standard enthalpy of formation? Okay, so I got a head nod there. Yes, yeah, it does. It produces 1 mole of water, and hydrogen and oxygen are in their normal states, what we would expect. Excellent, nicely done. Okay, how about B? Let's try B. I absolutely love this sweater. That is that is awesome. I love that sweater. Okay, so for B, does that look like it follows our definition of standard states? What do you think? What's tripping you up? What are you thinking? The carbon. Yeah, we've got carbon there as graphite. It's like, yeah, is that normal? Is it not normal? I mean, we think about nitrogen and oxygen all the time, but we don't think about carbon all that much. So is carbon normally graphite at room temperature and pressure? Yes. Okay. So B, does B fit our definition? Yes, it does. Okay, now we have other forms of carbon, like diamond and buckyballs and graphene and such. Diamond, we've seen diamond at room temperature and pressure. Is it normal, I guess is the question. It takes a lot of pressure and heat to turn graphite into diamond. So we don't think of diamond as really being in a standard state of carbon. It's an unusual form of carbon. Okay. All right, so nicely done. You've correctly identified this, that is this enthalpy of formation. Okay, well done. So let's try over here on the left-hand side here. Here, could you help me out here with C? Reaction C, what do you think about that one? No, so why not? Yeah, so there's 2 H2Os on the right-hand side, and by definition, we can only make 1 mole of one product, right? So can't be C, nicely done. And then how about a little further back there? Oh, Minnesota. Yeah. Excellent. So it would be, can't be D, because there's 4 moles of the phosphorus well, you even got the name right. I struggle to say the word phosphorus trichloride. Yes, nice. Yeah. For a enthalpy of formation? Okay, to have two products. No, it should only have one product. So somebody asked that in the 8 a.m. class. They said, Professor Locken, what if I have half a mole of each of these? Like say C, you've got carbon dioxide and water. What if you have a half a mole of each of those? Those together add up to 1 mole, and the definition is 1 mole, right? Is that good? No, it has to be 1 mole of one product. Maybe I should say 1 mole of one product. Okay. Okay, nicely done. Good question. Okay, any other questions? Okay, all right. Now in your textbook there's a table that looks similar to this, and on it we can see a lot of different compounds and then our enthalpies of formation. We don't need to memorize these, but notice that some of them have a value of 0. That is to say, it takes 0 energy for those molecules to come together. So as we look at these, see in the top of this left-hand column here, we've got oxygen, then we have hydrogen, they're 0. That's saying it takes 0 energy for oxygen atoms to be oxygen gas at room temperature and pressure, because they're in their standard states. So there's no reaction happening there. They're there already. They're already there. So some of these have a value of 0. And I'm just thinking because, I bring this up because at some point you might have a question that asks you, okay, what's the enthalpy of formation of this compound? And it doesn't give you a table, and you're thinking, I didn't memorize all of these, and that's okay, because you look at it and say, oh, well, if it's water in its liquid form, oh, no, water in this gaseous form, oh, wait a minute. That would be, oh, no, what am I thinking here? No, oxygen. Okay, oxygen, gas, it's in its standard state. So it's the way that we would expect it to be. Okay. So what do you do with all that? Well, there's a couple of things you can do with it. Here we have a chemical reaction. In the bold, here we have methane plus oxygen gives us carbon dioxide and water. And then down below it, A, B, and C, we have 3 different chemical reactions. These are enthalpies of formation. Notice the F's there, enthalpy of formation. Does this look kind of like Hess's law? It's like you have a chemical reaction and then you've got some other ones. And so then the question is, could you rearrange those bottom 3 equations to somehow add up to that top one? And the answer is yes. Yes, you can. So if we were to take those 3 equations, equation A, we would reverse it. Equation B, we leave it the way it is. Equation C, we multiply it by 2. And then we cross out things that appear on both sides. And we'd end up with that bottom equation. And we go, huh, okay. So you can use enthalpies of formation to find enthalpy of reaction. In this case, burning or combusting 1 mole of methane and 2 moles of oxygen gives us, or releases 802 kilojoules. I'm just going to write this number down. Releases 802.3 kilojoules per mole. Okay, so that's how much energy is released. Notice the sign is negative. Is that endothermic or exothermic? Exothermic, energy is being released. Excellent, okay. So we can use enthalpy of formation to find enthalpy of reaction. And we could go about it a slightly different way. And that is, we could use this equation here. Now the equation itself looks a little intimidating. There's like all these weird symbols and stuff in there. And when I took math, I thought I was pretty good at math and things were moving along pretty good. And then we ran out of numbers and they started using Greek because we ran out of numbers. And that's when math got hard. It became challenging. So I'm going to write this equation here and then we'll interpret it. So we have enthalpy of reaction is equal to this funny looking symbol here and products minus this funny looking symbol here again and N reactants. So some funny looking symbols there. And we know that this is enthalpy of reaction because it tells us reaction here. And we have this degree symbol here. That's telling us that it's at standard temperatures and pressures, which we'd say is 25 degrees in 1 atmosphere and such. Okay. What does this stuff mean? What does this funny looking E symbol mean? It means the sum. Okay, so the sum of something. And then N is moles. Okay. Now sum. When you sum numbers, you add them together, correct? Where this is all going is, oh yeah, we're adding up numbers here. We're going to add some numbers. That's where this is going. Okay, so we're going to add some numbers. Now we've got this chemical equation. We've got, let's see, we've got CH4 gas plus 2O2 gas gives us CO2 gas plus 2H2O gas. All right. And we want to figure out how much energy is involved in this. What is our enthalpy of reaction? So we'll say our enthalpy of reaction is equal to some number. Now we have enthalpies of formation. We have some enthalpies of formation. So if we go back to this table here, this table, we can pull numbers off of here. And we could say, okay, our enthalpy of formation for oxygen is 0. That was easy. And then methane. We find methane here. Methane gas is negative 74.8. Negative 74.8. And then carbon dioxide we look up here. We find top of this one here is 393.5. 393.5 negative. And then our water gas is 241.8. So negative 241.8. And there's 2 of them here. So I'm going to go like this, times 2. And then, this one here is times 2, but it's 0 times 2. So we could probably ignore that. Now it tells us it's the sum of our products minus our reactants. So here I have my products. And then over here I have my reactants. So I'm really just going to flip-flop these two. I'm going to take my products and I'm going to subtract my reactants. So I'm going to rewrite this and I'm going to say negative 393.5. And then add a negative 241.8 times 2. Okay, those are my products. And then I'm going to subtract from that. I'll subtract from that then my reactants. And so that will be a negative 74.8. And then add to that 0 times 2. Like that. Okay, so then if I do the math on that, I'll get some answer. And if you got a calculator, you can follow along. But, I'm going to give you the answer. The answer on this is negative 802.3, and that would be kilojoules per mole. Thank you. Does that number look familiar? Oh, we did it 2 different ways and we got the same answer. We did Hess's law, and then we also did here with just our straight up enthalpies of formation. Like, how about that? Coincidence? Maybe. Now, you're saying, but Professor Locken, is there another way we could do this? Oh, okay, okay. Well, just hold on just a second here. Let's try this. Okay, so going back to this problem here, where we have our chemical equation is methane plus oxygen gives us carbon dioxide and water. This is an energy diagram. And what this is showing us here is how much energy does it take to break bonds and to bring bonds back together again. So for example, on the left-hand side here, we have methane and oxygen, CH4 and O2. And we pull all these atoms apart. It's like breaking all the Tinker Toys here. Pull all the atoms apart. And at the top there, those are all the atoms that have been pulled apart. So they're not connected to each other. How much energy does that take? Well, we've got 4 carbon-hydrogen bonds. And then we have 2 oxygen-oxygen bonds. And it shows us how much energy is involved in doing that. To do that, we have to add 2,648 kilojoules per mole. We break all of those atoms apart, and then we put them together, and we form carbon dioxide and water. Together, these release 3,450 kilojoules. The difference between these two comes out to a total of 802 kilojoules. Remember that number? Where have we seen that number before? So up to this point, we've solved this problem using enthalpies of formation and Hess's law. Now this is going to be the third way that we can do this. This is going to be bonds breaking and bonds forming. And we have a new equation for this. Enthalpy of reaction is equal to the sum of the bonds breaking minus the sum of the bonds forming. And to use this equation, what we're going to have to do is we're going to have to see what all the bonds look like. This example here, we're going to take ethanol and combust it with oxygen to produce carbon dioxide and water. The result of this is going to release some amount of energy. And that energy we can calculate by taking a look at the bonds that we break minus the bonds that we form. But to do this, we have to be able to draw out the Lewis structures. So I'm going to start out with just writing the chemical equation. That's CH3CH2OH plus oxygen. And that gives us CO2 plus H2O. And I better balance that there and like that there. Now to draw the Lewis structures, we have some clues in the way that this is drawn, are written. We've got CH3, so that's going to be 3 hydrogens attached to a carbon and 2 hydrogens and an OH. And so this goes back a little ways, kind of jogging our memories a little bit, writing Lewis structures. But we're going to have a carbon and 3 hydrogens, like that, attached to a carbon and 2 hydrogens, and then an OH. And then we're also going to react that with 3 oxygens, like that. That is going to then give us 2 carbon dioxides and 3 waters. Like that. So here's all of our Lewis structures for these molecules. And now what we need to do is break that down into their constituents, all of the bonds. So here, for example, we have carbon-hydrogen bonds, and there are 1, 2, 3, 4, 5 of those, so 5 carbon-hydrogen bonds. And then we also have a carbon-carbon bond here, carbon-carbon bond, like that. And then we have a carbon-oxygen bond, and we have an oxygen-hydrogen bond. All right. Now here we have 3 oxygen-oxygen double bonds. Here we have 2 times 2. This is 4 oxygen carbon double bonds. And then here we have 6. We have 6 oxygen hydrogen bonds. 6 oxygen hydrogen bonds. Now, the energy involved in each of these bonds we can look up. And so we have tables here, like here's one from our textbook that shows us how much energy there is in each one of these bonds. And so if we just take all of these energies and we take our bonds breaking minus our bonds forming. So what we're going to do is we're going to write out each of these energies. And so for our bonds over here on this side here, we're going to have 5 times 413. So I'm just going to say 5 times 413. 5 times 413. And our carbon-carbon bond, that is 347 kilojoules per mole. Our carbon-oxygen bond is 358. And our oxygen-hydrogen bond here is 463. Okay. And if I add all of those up, I get 3,233 kilojoules per mole. Now over here I have 3 times 498, and that then gives me a total of 1,494 kilojoules per mole. My 4 oxygen carbon double bonds here, that's going to be 4 times 799. And so that gives me 3,196 kilojoules per mole. And then my oxygen hydrogen single bonds over here, that's going to be 6 times 463 for a total of 2,778 kilojoules per mole. So what I'm going to do now is I'm going to take these two numbers, add them together, and then subtract. So take these two numbers, add them together, subtract the sum of these two numbers here, and that should give me my total. And when I do that, I end up with a negative 1,247 kilojoules per mole. 1,247 kilojoules per mole. Now what we want to do from here is figure out what is the fuel value. And the fuel value is measured in kilojoules per gram. And so I'm just going to take this and I'm going to convert this into kilojoules per gram. So I have a negative 1,247 kilojoules per mole. Kilojoules per mole. And my molar mass for ethanol, if I were to add up all of these carbons, hydrogens, and oxygens together, I get 46 grams per mole. And so when I do that, I end up just taking this 1,247 divided by 46, and I get a negative 27.1 kilojoules per gram. And so that gives me my fuel value. Fuel value of ethanol. Now we can compare this to other sources of fuel, such as diesel fuel or gasoline. And when you take a look at these different fuel values, you notice that ethanol has a lower fuel value per gram. And so where does this apply in the real world? Well, in the United States, we're taking corn and we're fermenting the corn to make ethanol. And then we add that ethanol to gasoline. About 5%, maybe 10% or 15% ethanol in our gasoline. And when you notice that the difference in the fuel value here, it's less than gasoline, what do you think that does then to our fuel economy? What do you think that does to our miles per gallon? Or maybe I should say our kilometers per liter. right? Yeah, it ends up lowering our fuel economy. We get fewer miles per gallon when we add ethanol. And so this is one of the reasons why we only limit our ethanol in our gasoline to maybe 15%. Have you ever heard this phrase, add up these numbers? Have you heard this before? You've heard this before. So, for example, if I have, say, 10, 5, and 7, like this, and I say, add up these numbers, where would you write the answer? Up or down? You write the answer down, but I told you to add up. Oh, am I the only person who stays up late at night thinking about stuff like this? What's up with that? So as it turns out, the people who used to do this were the Romans. And the Romans, when they would add up numbers, they would put the answer at the top, up here. It's just us that puts it at the bottom. So the Romans would put it up here. And they called this here, they named that after this thing. It looked like this. It was a mountain. And what do you call the top of the mountain? The summit. The summit, it means the top. And so when you sum numbers, you are summiting numbers. It's just short for summit. So you are putting the numbers at the top. Now that carries over into English. And we say, add up these numbers. And it's like, what? Where does that come from? It comes from the old Latin. Okay, another ADD moment for you. Okay, stupid story. When you understand what somebody is saying or they're thinking, do you ever say, I see what you mean? I see where you're coming from? So in Latin, to see is video. It is spelled V-I-D-E-O. V-I-D-E-O. And it means to see. And that verb, to see, in Latin means I understand. The O ending means I understand. And that carries over into English today. So when we say I understand, I see what you're getting at. That comes from the Latin for I understand. Okay. What does that have to do with this? I don't know. Where was I going with this? Okay. Matt, we're going to have to edit that out. Okay. So where